Capture of how to do the calculations that you need to do for Project 1, and also the kinds of calculations that you'll see on tests. And since people are nervous about doing calculations, and I said that there's not going to be a lot of math in this class, what I want to do is to go through several and make several examples so that you'll have something to follow. So if you go to that link, you'll find a communication diagram that looks like this. This is what I'll be working with, and what this basically does is talk about two different speed connections that are usually used in for consumer connections to the internet. Now they're really old, and communication speeds change all the time. Not many people use dial-up anymore, although if you live out in the middle of Wyoming and you don't have enough money for a satellite link, dial-up is the only way that you can get in. And once you get outside the United States, you'll find a lot of places that still use dial-up. So it's a useful example because it's asymmetric, just like ADSL is. The difference is that the speeds are much slower, which it'll also give you an insight into why you didn't upload movies into the internet back in the early 90s, because it would take a week and a half to upload the silly thing at dial-up speeds. So both of these are asymmetric. The dial-up asymmetric means the speed in is different than the speed out. The reason for that is that in the early days of the internet, it was thought of as a resource where you type in a request and then a bunch of junk would come back out. So clearly you didn't need much bandwidth going in because the requests are relatively short, but you needed bandwidth coming out so that you could receive all the information that you'd asked for. And that's the reason for asymmetric. Now with dial-up, the going in speed is 33.6 thousand bits per second, 33,600 bits per second. The speed out is almost twice that fast, 56 kbps or 56,000 bits per second. Now that's dial-up. ADSL is a huge improvement. It's almost 20 times faster going in. Going in, it's 640 kbps or 640,000 bits per second. And coming out, it's like blisteringly fast comparatively. It's, what is that, at least 10 times as fast as going in. At 6.1 Mbps, millions of bits per second, so it's 6,100,000 bits per second. So that's two different connections, two different speed asymmetric connections into the internet. So let's look at some of the problems. Basically, you're going to run across three different types of problems in this class that deal with file size and transmission speed. The first one is, how big is a file given the sample rate and the quantization level? The way you calculate that is you take the sample rate, you multiply it by the quantization level, you multiply it by the number of tracks, either one for mono or two for stereo, and then you multiply it by the recording time in seconds, and that should give you the file size. The only trick to these is to make sure you get the units right, because from a previous lecture you probably remember that the transmission speeds are expressed in bits per second, and the file sizes are expressed as bytes. So if you're trying to use a file size in bytes and a transmission speed in bits, they don't match. You have to match them up. So we will be covering how to do that in the examples, but just keep that in mind. Second kind of question is, how long will it take to upload or download a file of a certain size? So if you have the file size, you can divide it by the transfer rate, and that'll give you the time to upload or download. Once again, remember that file size is usually expressed in bytes, and transmission speed or transfer rate is usually expressed in bits per second. So there's a mismatch there that you have to correct, and the examples that I go through should do that. And the third type of example is, given a particular file size, a file of a certain size that was recorded at a certain sample rate and a certain quantization level, how long will that file play if opened with QuickTime? So what's the play time? So you're kind of backing into that answer. And the first thing you need to figure out are the number of bytes added per second of the recording. So if you've got the file size, you know how big it is, and you know how many bytes per second are collected, you can divide the bytes per second into the file size, and that'll give you the number of seconds the thing will play. So it involves two different things. You take the sample rate, multiply it by the quantization level, multiply it by the number of tracks, and that'll give you the number of bytes added per second of recording. Then you simply take the file size and divide it by the number of bytes added per recording, and that'll give you the length of time that this will play. So we're going to go through examples of all of these, and we're also going to have an additional example, two examples that talk about that involve Nyquist rate conversions. So